All right, welcome to part 2 of our trip to a black hole. So this time we'll be crossing the event horizon and looking at special cases that we might think there are black holes in our galaxy and the universe. So this is Extraordinary Concepts in Physics, where we try to focus on the concepts and not the math. It's Physics X being taught at Michigan Tech for credit. You can find all these lectures online, of which I think there's over 25 now and growing. Online, either at iTunes or through Starship Asterisk. Search for Physics X, and you can watch these at your leisure. So, reviewing some key concepts of a trip to a black hole, some key distances as you fall in. When you're far away, you feel no gravity at all, and when you're infinity. It's called flatness. There's no curvature effects at all. When you start getting near the black hole, you will start noticing that there is Newtonian gravity, and you don't notice anything different. You wouldn't be able to tell the difference between Einsteinian gravity, which admits black hole solutions, and Newtonian gravity, which doesn't, because Newtonian gravity is somewhat coupled with the idea of infinite speed of light, and so you wouldn't have a black hole. But when you get closer to a black hole, you notice that the acceleration might differ from standard Newtonian gravity. You have to get pretty close. Then when you get really close to the black hole, 3 times the Schwarzschild radius, you realize that that's the last stable orbit, and that you can't just keep it to an orbit that keeps returning to itself exactly all the time inside of that. You might spiral in or spiral out. When you get to 1.5 times the Schwarzschild radius, which is the event horizon radius, photons can do circles there. So photons are moving as fast as things can go. When you pass this, which we will be going to a little bit past here, that's the event horizon, that's the point of no return. You're then disconnected from the outside universe. If there's a singularity at the center, then you might come into within the Compton radius, where quantum mechanical effects will become important, and we really can't say what happens too much closer to the central singularity of the black hole than that. If for some reason you could turn quantum mechanics off, you could then say there is a central singularity at r is equal to 0. All right, so let's keep descending toward the black hole, so descending to the event horizon. So as you descend to the event horizon, the visible universe will scrunch up on top of you in the direction opposite of the center of the black hole. And blackness will be the rest of the way. So first you start, and the black hole is just a circle in front of you of blackness. Then when you hit the photon sphere, half of your horizon is black. Everything toward the black hole is black, and everything in the opposite direction is still the rest of the universe. But it's now bluer and moving faster than before. So as you go closer and closer to the event horizon, the universe just scrunches up into a little skylight at your top, where it's now raining down X-rays and gamma rays, where it used to be just low-energy photons before. And finally, when you cross the event horizon, that little hole would remain just a point, would go to a point. Okay, so I described this. Clocks run increasingly fast as you get closer to the event horizon. So you will see infinitely many versions of the universe as you go toward the event horizon. Just as you cross it, you can see lots and lots of Einstein rings, and between Einstein rings or image sets, you see lots of versions of the universe as you fall in. One surprising thing. Let's say you did all of this in one of our elevators or in a closed room where you're not seeing the outside universe. You yourself might not even notice that you've passed the event horizon of a black hole. Now, if the black hole had relatively low mass, meaning like a star, like our sun, if we can compress our sun to a black hole, there would be tremendous tidal effects which would rip you apart, and there's nothing you could do about that. But if you could go near a black hole that has the mass of, say, a galaxy or like that, then the local effects of going near a black hole, the tidal effects, would become increasingly small. And you would be outside the event horizon. If you couldn't see the outside universe, you would be at the event horizon. You'd be inside the event horizon. You wouldn't yourself notice any difference. You would just keep eating your chocolate pudding. No difference. They'd have to tell you. It would have to come over the announcing system, the PA system. Attention, everybody, we've now passed the event horizon of the black hole. However, at that point, your relatives out there, they're disconnected from you. You cannot go back and visit them. One slight humorous note, the microwave background radiation and even starlight that we enjoy here as interesting and fun would be raining down on you with increasing energy as you got closer to the event horizon of the black hole and even inside, so it could be potentially dangerous. You would need to be protected from the very high energy microwave background. Would no longer be microwaves, would be gamma ray background that would be coming at you from above. So as I said in previous lectures, you can't move outward anymore, you can only move inward, but since everything's moving inward, you don't really notice any difference. If you'd like to come up with a clever scheme saying, I know what I'm going to do, I'm going to hold on to a rope that is anchored outside far away, and then once I'm inside the event horizon, I'll pull on my rope and signal a distant friend to pull me back out. What you find out then is that the rope would have to be infinitely strong, which nothing is. And since nothing is infinitely strong, as you cross the event horizon, the rope to outside infinity must break. Another thing is that when seen from far away, people falling toward a black hole will appear to move slower and slower, and then their image disappears as they go inside the event horizon. However, if you're enjoying your chocolate pudding right there, falling in yourself, you don't notice any time difference of yourself. So if you look at your wristwatch at infinity, it runs at the same speed as when you look at your wristwatch just above the black hole's event horizon as when you look at your wristwatch just below the black hole event horizon. So also, no one has ever really done this. So this is a conjecture of looking at the equations of general relativity and figuring out what things would look like, what trajectories would be, how relative time slowing would be. So this is conjecture. So what happens as you pass through the event horizon of a black hole depends on what the mass is doing inside of that. There are some theorems that say that after some amount of time, the black hole would have to the mass would have to condense at the center. However, it's possible to take a neutron star and turn up the mass such that from infinity, a boundary is crossed for what looks like is a black hole inside. And then you would be in a place where there's actually constant density. Also, you might have noticed, as I said in a previous lecture, that the average density of our universe would be the average density of a black hole the size of our universe with the mass of our universe. So we could be living inside a black hole. So there are non-singular solutions that could occur for some time. So we don't really know what's going on. If you fall into a constant density neutron star solution and you're not destroyed by the high density of the neutron star, things would actually become more Newtonian as you went to the center and there would be less curvature effects. If there is, however, a singularity, then, and I said you don't need a singularity for an event horizon to exist. As you go toward the central singularity, you will increasingly, eventually you'll have to become, quantum mechanical effects will become important. And you can reach that singularity in a finite amount of time. So another possibility, some people think it would take an infinite amount of time to fall to the black hole singularity. No. Although whatever clock is falling would be destroyed, you could hit the singularity in a relatively short amount of time. So you should eat your chocolate pudding quickly. You would first hit the Compton radius, at which point quantum mechanical effects would be important. And we don't know what those would be. Before that, possibly, depending on the mass of the black hole, you would experience tidal effects. If you didn't experience, tidal effects could occur anywhere. They could occur outside the event horizon, they could occur inside, but that could rip you apart. So let's see, as an outside observer sees someone falling in, again they get more and more red until they cross the event horizon, and then they disappear. However, when gas falls in, so if you have a black hole here, let's make it black, and you have gas falling in, that's here. As it gets near the black hole, it collides with itself and then heats up. So strangely enough, if you have a black hole in the universe that's surrounded by normal gas or an accretion disk, you would not look for a black spot in the sky in optical light or even X-ray light. You'd look for a bright spot on the sky because the mass that is falling in is colliding with itself and heating up, and because it's hot, it emits lots and lots of photons that go out to infinity. So black holes in the normal universe would not look black. That's because we're seeing the stuff that's outside the event horizon heat up. All right. So there are several well-known cases of objects that are so dense that we don't know what else they could be besides black holes. Cygnus X1 is one, something called V404 Cygnus is one. In fact, the center of most galaxies, we see stars moving fast enough, and we see that it's a very high mass object there. So we hypothesize that the centers of most galaxies, including our Milky Way galaxy, has a very massive black hole. It's also thought that when some explosions occur, like some supernovae explosions, particularly some explosions, some types of gamma ray bursts, that when a tremendous explosion occurs, it might be signaling, oh, there's going to be a black hole here very soon. Okay, so here's a picture of the center of our galaxy, and the black hole here, let's go to blue, is sometimes called Sagittarius A star, is thought to be inside this region. And there are strange things happening around here. Strong magnetic fields effects. So the very center of our galaxy, this is not an optical image, I think this is a radio image. So here's a supernova star exploded. There's a lot of stars in the area, a lot of hot gas in the area. A lot of things that are not really well known. There's some kind of coherent structure. No one's quite sure what that is. So we're still investigating the very center of our own galaxy, which is thought to have a black hole. Okay, this is a zoom in from the previous image, so I'll show you where that is. So if you look at this here, connected to here, that's what you're seeing. So the next image is going to be just about this. Ready? Got it pictured? Oops. There you go. So this is the galactic center radio arc. So these are gas strung along magnetic field lines. This is Sagittarius A star. So inside of here, it appears that there is probably a black hole. But it's the bright gas is emitting not only X-rays and gamma rays, but also it's radio bright. So if you look in the right kind of infrared, you can see stars moving. And so here, this is actual data. So I think the center, black hole at the center of a galaxy is given by the plus. The stars are actually much smaller than the white ovals that you see. It is due to the point spread function, the fact that we can't resolve down that far. So when you look at stars at night, you're not actually seeing the disks of those stars. You're seeing them spread out in our atmosphere. So the telescope itself is spreading out these star images to be much larger than they really are. So this star here is not going to hit the black hole. It's going so close to the black hole that you can't tell the difference with this telescope. But what we can see here is that these stars out here are moving very slowly, but stars near the center of our galaxy are actually moving very quickly. And so this is evidence in itself that there are black holes, that there's a black hole in our galaxy center, because you ask yourself, if this was a large object, then it should have hit the edge of this large object. So there is a relatively dark object in the center that's not emitting a lot of light, that's very compact. And you can guess how much mass it is by how fast these stars are moving by, and it gives us an estimation that this must be some sort of black hole. Now here's a little bit of a movie. This is now, instead of data, this is animation of the stars very near the center of our black hole. So you'll see flashing on there where the black hole is supposed to be in the very center. I think it's just about here. Let's go to red. It's here. And so these stars are extrapolated in this animation from where we see them, and they are orbiting around the black hole. And you can see these stars move a little bit in the previous frame, which you can back up with your cursor. So that's one of the things that we're going to, hopefully in the next few years, the next decade in astronomy, we're zooming in on the very center of our own galaxy, and we hope to get more and better information about the black hole there, and confirm maybe with images, that exact images, that it is even better confirmation that it is a black hole, and learn a lot about black holes and gravitational lensing from looking at the very center of our galaxy in the next few years. Okay, and with that, I will congratulate you for taking this virtual trip, and I'll see you next time. Thanks, bye.